because all my sections have been asking about test dates and stuff, so I want to make sure everyone has this information. Let's see. Today is October 27th, and today my plan is we're going to close out chapter 7. We're going to look at how specifically gravity acts as a centripetal force, and that'll close out chapter 7. That said, next week is still more rotation. There's 2 rotation chapters. So that's next week, the 30th through the 3rd. Week after that will be a short chapter on pressure and buoyancy. And then when that chapter is over, we will move into review period for the test, test 2, which takes place this highlighted week, November 13th through 17th. It'll happen during lab time again, so lecture time that week will still be reviewed for that test. There'll be a practice test too and everything like that. And it'll be on chapters 6 through 9, so momentum, rotation, and pressure buoyancy. My goal is we take it this week so that it's done and over with, and I power through and get graded by Monday the 20th so that we can take off for Thanksgiving and not have to think about it. When we get back from Thanksgiving, we'll have one more quick chapter on mechanical waves and sound before. That's the last new thing we'd ever talk about this semester, and then we move into exam review territory. Exam will basically be everything that we've talked about, chapters 1 through 9, and then a little bit of the sound, like one question about the sound and wave stuff that we cover in the last week. And the exam season starts Wednesday, I think? And this class's exams take place at different times on Thursday and Friday, December 7th and 8th.
They start Thursday, Wednesday's reading day.
Oh, okay, thank you. My mistake. Actually, I have the exam schedule here, so I will point out you were absolutely correct, and I misremembered.
Reading day's like when everyone does like capstone presentations, or we just don't have class that day for those reasons. I don't know how to describe reading day.
It doesn't, it's meant to be like a free study day where no one has any new
But a
assignments.
lot of times they'll do capstone presentations during that day.
That feels counterintuitive. I don't like that. What department chair role do I need to be in to change that policy? Just do it. Well, I don't have any capstone students, so I won't make you do anything that day. In fact, that Wednesday's the 6th, and they made all the homework due Tuesday the 5th. So ideally, you wouldn't even have any homework to do on that day. Anyway, for this class, and I'm just addressing it now since it's on my mind. I teach 3 sections of this class, C, E, and F, which is this one. And it's all the same lecture 3 times in a row, and it's why I don't care which lab day you come in to take the test. So I also don't care which period you come in to take the exam either. So C period for the exam is Thursday the 7th at 5:30, bless you. F period is 8:30 a.m. on Friday the 8th, and E period is 5:30 p.m. the same day. Of the 3, I don't care which one you come in and take the exam, as long as I have space in the room. So officially this one's is 8:30, but I have to be here. You can choose to show up at a different one if your schedule allows for it.
What if we show up and the room is full?
Then I'll make something up.
Okay. We can use the
Formula sheet? Yes. Calculator and formula sheet. And you can ask me questions, same as the tests. I've got all those 3 times written over there, and they'll just remain there till the days come. So, exam, any of those 3 days. Test, any of these 4 days. Remember, Thursday's a myth. There's no lab on Thursday. And any questions or issues with the upcoming schedule? All right. Any questions about anything at all before we get started? Serious or otherwise?
So all classes have the same like period letter, right? Like last hour with the E.
Yes.
I have 2 tests that day.
There we go. Yeah, it's not great. I feel like which days go when is kind of arbitrary, and it's technically possible for someone to be doing nothing but exams all in one day. So I think it's in need of revision, but at least we are told that the exam is meant to only take 3 hours max. And ideally that leaves you an hour between all of them, but still, you got a lot to do in that 1 hour.
I guess New York and chemistry is same day.
That's not fun. Well, you could do it Thursday if you wanted, or is that the day you're talking about it? Alright.
I thought we had to do it on Friday, December 8th.
Okay. Well, again, those are the 3 that are already scheduled. Whatever's best for you guys. I have to be here all the time. Doesn't mean you have to. Anything else on your minds for right now? All right. Well, today we're going to get spacey. Look at how gravity acts specifically as a centripetal force in space, which we've talked briefly about. If you recall, as we were defining centripetal force earlier this week, we did acknowledge how the force of gravity between the Earth and the Moon is what acts as a centripetal force on the Moon and causes the Moon to rotate the Earth. And that's true of every orbit in space. Moon around Earth, space stations around Earth, Earth around Sun, all that stuff, all that good stuff. The force of gravity acts as a centripetal force. That means you can usually set the 2 equal to each other. The problem is, how do you calculate force of gravity in space? Historically, how have we calculated force of gravity? It's not a trick. It's the same as question 1 on the first test. How do we usually find force of gravity in here?
Mass times G.
Yep, just mg. And g in this case is defined as negative 9.8 meters per second squared. Does this work in space? No, and that's because that negative 9.8 is very specifically the acceleration of gravity on Earth's surface. Meaning that number stops working if you aren't even on Earth's surface. You can climb a mountain or, I guess if it's possible, dig yourself down as close as you can to Earth's core without dying, and that number isn't true anymore. It very specifically is only surface level gravity. So it's definitely not true of the Moon, which is even, this is not a scale drawing. The Moon is very far away. I want to make that clear right now. Earth is here, Moon is here, satellites are like right here. That's why getting to the Moon is hard. Moon is too far away for that 9.8 to work, and so we need something else. So rather than looking at gravity as just the thing that holds us to Earth's surface, we now need to define gravity in more general or universal terms. So to that end, I present to you the universal law of gravitation. That is the name of this formula. When I say universal law of gravitation, that is this formula's name. And what this law states is that all objects with mass exert gravity on each other. And the force of that gravity depends not only on the masses themselves, but also on how far apart they are. All objects do this. If it's made of mass, it is actively creating a gravitational field. And that does include your own body. You have gravity. It's just very weak because you don't have the mass of a planet. But all objects do it, and the purpose of this formula, referred to as the universal law of gravitation, is to find that force between any 2 objects regardless of mass or distance. So its function is, kind of very usefully, figuring out the gravity between any two things, even if one of those things is an Earth, and even if you are not on Earth's surface. Yes?
Is that a variable x or multiplication sign? On 6.6?
Oh, that's x. That's multiplication. My apologies. Yeah, this is 6.67 times 10 to the negative 11th power. Apologies, sorry. So, all objects with mass exert force on each other. And this formula says that that force between any two things, this is force of gravity, so this is still measured in newtons. There's no actual new units or anything here. This is just a new way of finding the force of gravity. Force of gravity between any two things, bless you, is equal to big G, which is its own constant, I'll address it in a minute, times the mass of the first object times the mass of the second object. So you need the mass of both things in kilograms, and they do get multiplied together. So the mass of both things matters. Both masses multiplied together, and then divided by radius squared. And this radius represents the distance between the centers of mass of each object. It's just how far apart they are. You do not say, set two things 1 meter apart, and then say, oh, it's radius, so I cut that meter in half. You don't do that. It is the distance between them. And we call it radius because say the distance between the Earth and the Moon, for example. We call it radius because it is the radius of the giant circle that represents Earth's gravitational field. And also, coincidentally, it's the radius of the circle that the Moon forms when it orbits the planet. So that's why it's called radius. You don't take this length and cut it in half. It just is this length. And those are the factors that determine the strength of gravity between any two things. This is why Earth's gravity is the strongest gravitational force you will ever consciously experience, because the Earth is massive and you're standing right on it. You're very close to it. The masses are both situated in the numerator, so the bigger the mass is, the bigger the gravity. Meanwhile, R is on the bottom. So if R gets bigger, if you get further away from Earth, what happens to the force? It gets smaller. Divide by a bigger number, you get a smaller answer. So when you leave Earth, gravity gets weaker. Meanwhile, if you get closer to the center of the Earth, gravity goes up because you're dividing by a smaller number. And this is why the center of the Earth is on fire. There's just so much gravity down there that immense pressure causes the objects to superheat and liquefy. So, weaker if you go up, stronger if you go down. But that distance thing is also handy because it points out why you don't really notice the gravity from other objects in space. Pluto exerts gravity on your body because you and Pluto both have mass and you are some distance apart, but you are so far apart that that number is negligible. Questions so far? All right. Some quirks about this formula. One, you do want to make sure you're using kilograms and meters. G stands for this constant specifically. Note that uppercase G is different to lowercase g. I apologize if that is confusing, but the case matters. They are different constants. Uppercase G is called the universal gravitational constant because its only use is to make the universal law of gravitational formula work. This is the only time it is used. The purpose of this constant is just to make the formula work right. And for that reason, it's on the formula sheet with the formula. Right about here, force of gravity is where the formula is, and right beneath it is G. So you don't have to memorize it. This is its only use. It does technically mean something. relates to the permittivity and permeability of free space, but that's not on this course syllabus, so you don't have to worry about it. For this course, it's the number that you need to make the formula work. And this is one of the big things that Newton was working on. He was not the first person to ever discuss gravity, but his work got very famous for it. So Newton did work figuring out this constant to make the formula work right. Lastly, I'll point out that whatever number for force this formula gives you acts on both objects. It's the force that one pulls on the second with, and likewise, it is also the force that the second exerts back on the first, because of Newton's third law. If one acts on the other acts back on the first. So if you use this formula and get like 10 newtons between two objects, they are both being pulled inwards by 10 newtons. That force is one on the other and the second on the first as well. Equal and opposite, net direction inward for both. Does that sound okay for now? All right. Now this is a new formula, so let's practice it a little bit. I did say you can use this to find the gravity between any two things, so let's find the gravity between these two things. 10-gram markers situated about 10 centimeters apart. As long as they have mass, they are creating a gravitational field, and we can figure out how strong it is. It's not going to be very big, but that's what we're going to prove. So our new formula says, force of gravity between any two things is big G times M1 times M2 over R squared. So in the case of those markers, they both have a 10 gram mass, and they are situated 10 centimeters away from each other. So, big G is and will always be 6.67 times 10 to the negative 11th. And then we've got the two masses. They'll be the same number here because the two objects have the same mass, but that's only true if it's two objects that share a mass. Usually if they have two different masses, it's two different numbers. 10 grams, how many kilograms is that?
0.001.
That is one too many zeros.
0.0. That's what I have right now.
It's all right. Yeah, 10 divided by 1,000 is 0.01. Again, same mass, so it's just the same number twice. Bless you. Lastly, distance between the two objects squared. They're 10 centimeters apart. How many meters is that?
0.01.
Once again, still too many zeros.
You said
Centi is 100,
Okay.
not 1,000. So 10 divided by 100 is 0.1. And then that 0.1 gets squared. You want to make sure you're only squaring the 0.1. Sometimes this formula has some calculator weirdness. There's scientific notation in it, there's a squared in it. So quickly I want to write out how I would input this in my calculator. I like to use the E button that it sometimes uses when it gives you an answer. So the E just means times 10 to the power of negative 11. Then 0.01, 0.01 again, divided by, open parentheses, 0.1 squared, close parentheses. So that's how I do it. And if you do all that right, how much force do you get?
6.67 times 10 to the negative 13th.
Correct. And it's still a force, so it's just measured in old-fashioned newtons. that force is too small for your nervous system to detect. This is not even enough force to make your arm hairs twitch. So you will never notice it. It exists, it is just too small for the human sensory experience to capture. Furthermore, since we live on planet Earth, where we are constantly surrounded by air and having to deal with friction from the ground, these two objects will never draw near each other because of that force. They are exerting that force on each other as we speak. However, all the friction pulling them in every other direction is more than enough to hold them in place instead.
So say they're in space, would they bring themselves together?
Yes, very slowly, but in the vacuum of space with no friction and no other nearby objects to create stronger gravity, they would eventually drift closer together until they just are stuck. And this is the leading prevailing hypothesis for how planets and stars are formed. Over time, objects in space just tend to drift towards each other, and eventually they get so close to each other that they just start lumping together into giant balls of rock and or fire. Questions about that one? Now, before moving on to the next one, I kind of just want to, I'm not going to redo anything big, I just kind of want to tweak something slightly to build the sense of scale a little bit. Let's say instead of the force between two markers, we find the force between me and this marker. Because I have a much bigger mass, maybe my gravity will do something, right? So my mass is approximately 100 kilograms, which is about 10,000 times bigger. So maybe we'll get a bigger number. We're using a mass that's about 10,000 times bigger, so the answer is about 10,000 times bigger. And that's going to change the final answer from 10 to the negative 13 to 10 to the negative 9. Still too small. Still not enough to twitch an arm hair. So your own gravity will never be something that you consciously notice, unfortunately. Well, maybe fortunately, it would kind of suck if everything stuck to you all the time. So, unless you're a planet and have the mass thereof, your own gravity is likely too weak to do anything noticeable unless you are free floating through space and have millennia to wait. Meanwhile, though, let's switch gears and look at something something on the scale of a planet instead. So here we have a 75 kilogram human standing on Earth's surface. Massive human, 75 kilograms. Massive Earth is currently believed by all of our best measuring tools to be 5.98 times 10 to the 24th kilograms. Single largest object you will ever interact with unless our space program gets very good in the next very short time. Even then, I don't think you'd really want to get anywhere near a bigger mass because it would probably exert enough gravity to pancake you. So, we're using bigger masses this time, one of them phenomenally bigger. They're both in kilograms though, so we don't have to do anything with that. Then we have to talk about the radius, what radius to use. Right now, what is the distance between your surface and the Earth's surface?
Well, the concrete we're standing on, however thick that is.
That's fair. If you consider the concrete and the floor to be part of planet Earth, because they are attached, what is the distance between your surface and the Earth's surface?
0.
0. You're on Earth's surface. And if we input 0 here for radius, for distance between the two objects, what happens?
It doesn't.
It doesn't work. Dividing by 0 makes your calculator mad.
Makes a black hole.
I hope not. Yeah, dividing by 0 is not great. At best, it gives you 0 gravity. At worst, it tears open a hole in reality. So the distance between you and the Earth is not 0 meters right now. Because what this formula requires is the radius to be the distance between the center of mass of both objects. Most humans' center of masses tend to be somewhere in here, because it's the part of you with the most mass. In the case of the Earth, its center of mass is also its literal center. And since the about 4 feet from the floor to my torso is kind of negligible, the radius we want here is Earth's radius, the distance between its core and its edge that I'm standing on.
That's a big human.
Yes. Asterisk, not to scale.
Attack on Titans right there.
If this actually was something that could happen, like, you wouldn't have an anime. Like, a person this big would have their own gravity and the Earth would already be dead. Like, this is like phenomenally bigger than Godzilla, let alone anything in Attack on Titan. Person that size has their own gravity, they pull all the oceans toward themselves. People standing here would drift up towards their center of mass.
They have the force.
They have the force of gravity on their side. There's an argument that Jedi are just manipulating gravity because they say the force is a field everywhere, and gravity's a field that makes force. But for our purposes, not to scale, the radius we want is the Earth's radius, because that's the distance between its core and its edge that we're standing on. And Earth's radius averages out at 6,380 odd kilometers, excuse me, that number of kilometers. I mean, you can use kilomiles, it would be 1,000 miles, it's just you'd make everyone angry. Fun fact though, Earth isn't really a perfect sphere, it's actually kind of oblong. It's widest at the equator. So even this isn't perfect, because Earth isn't totally round. Your distance to Earth's center is not constant.
Can we get an extra point on future tests for using kilomiles?
I mean, if you are using them correctly, I wouldn't count off.
That's funny.
Extra effort.
If you use kilomiles correctly, I'll be impressed, and I would be more inclined to give your work partial credit and round up. How about that?
Okay. I'm not going to use kilomiles.
I wouldn't recommend it, but I'd be amused. So in this case, we need to take this many kilometers, turn it into meters, and then square it. So, very big number. So, meters to kilometers are 1,000 times bigger, multiply by 1,000, and then, again, be very careful to only square that number. And if you do all that right, you should get approximately 735 newtons. The issue there is sometimes numbers just don't come out of my mouth right. Which is a reasonable amount of force. It's literally the weight of a human. And to prove that it's the weight of this human, we're going to find the weight the old-fashioned way. M times 9.8. So, 75 times 9.8. Confirm with your calculator, shock of all shocks, it's 735. That is because G equals 9.8 was derived from this formula. Basically, they took this formula, they ripped out M2, multiplied big G times Earth mass over Earth radius squared, and got 9.8. So this is basically a boiled down hyper-specific version of the general rule. This is the general universal law of gravitation that always works. This only works between one object on Earth's surface. And that's why we cannot use it to find the weight of the moon. We're able to use this instead.
How much does the moon weigh?
That's what we're about to find out.
Ah.
Before that, questions on this particular number? All right. I will say that how much gravity any given planet has is a unique combination of its mass and radius. The moon has about 100 times less mass than the Earth, but its gravity is not 100 times weaker since its radius is smaller. So you are closer to its core than you are to Earth's core, and so that nullifies the difference to be about 1/16th of Earth's gravity instead of 1/100th. So any given planet's gravitational pull is a function of both its mass and its size.
What if it was the size of Earth with the mass of the moon?
Okay, Earth's size but moon's mass, it'd be 100 times weaker. If the radius went unchanged and the mass was reduced by 100, then it'd be 100 times weaker. But hypothetically, there's a perfect mass radiance balance out there where you could have a very tiny planet with Earth levels of gravity, as long as it's the correct mass for that size. On the other hand, you could hypothetically have a huge planet with Earth levels of gravity if it had a very small mass for that size.
Gas
So, we will now figure out the force the Earth exerts on the moon such that it acts as a centripetal force to make the moon orbit. This means we need the mass of the Earth, which we have from a second ago, 5.98 times 10 to the 24th kilograms. The mass of the moon, meanwhile, is 7.36, might have been miswriting that earlier, times 10 to the 22nd kilograms. Again, it's only really about 100 times smaller in terms of mass alone. However, its radius is very different, therefore the gravity equals out to about 1/16th of Earth's. So those are the two masses, very big numbers, so again, make sure you're inputting scientific notation correctly. Lastly, we need the distance between their centers of mass. The moon is on average about 384,000 kilometers away. Once again, we're gonna have to multiply that by 1,000 to turn it into meters, and then square it. The moon is very far away. It's our closest neighbor, but it's still not super close. If I was to try to make a somewhat scale drawing, it would look something like this. Humans, imperceptible, and our space station is right about there. Tiny little dot. It's actually very close.
That's why it takes 3 days to get to the moon.
Correct. And years to get to Mars. That's why getting to the moon is hard. That's why we haven't gone back. We did it a few times to prove we could, but it takes a lot of gas.
It's okay, man. We know cryogenics actually does exist with fish.
Correct, but fish are better equipped to handle that than humans
Well,
are.
they've been doing it before we did it to them. In frozen ponds.
Yeah, and there are loads of animals that just straight up get frozen in winter and survive it. Like there's frogs that hibernate by literally freezing solid. Humans are not built to do that, so to do it correctly to us, you have to take all kinds of weird steps, like replacing your blood with something else. And then, like, if you were cryogenically frozen on a spaceship, you would need all of the life support systems to be working correctly the entire time. And you would need backup processes in place such that if everything was going to heck and the station was malfunctioning, you need backup generators to correctly undergo the correct number of steps by themselves to wake you up, which would again involve replacing all of your blood with your blood again and warming you up slowly by themselves on backup power. I don't trust a ship to do that. You know how many things go wrong in space? Anyway, if you do this right, what number you get?
One of the senior seminar projects for bio right now is how tardigrades completely like dry out, and then you can put water on them and they come back life.
Does that include water bears?
That's what they're, yeah, it's really
Yeah, I've
interesting.
heard about that.
Supposedly, there's bacteria in the ice caps that have been dormant for thousands and thousands of years that will come back once it melts.
And global warming's melting all the ice. I mean, it's a good thing that the frozen mammoths aren't just straight up waking up, but the germs could be more dangerous.
And that's how we're actually able to bring back the frozen mammoths, is because we can get their DNA because it's been frozen.
Yes, get the DNA injected into elephant ovum.
Yep. Crazy. Oh, 1.99 times 10 to the 20.
Yep. This is a tremendous amount of force. If this force was acting on your body, you and your bones would be rendered flat. That is enough to powderize your bones. However, if you exert that much force on the moon, it just causes it to gently drift around the planet. So, a couple key things. This is the force the Earth exerts on the moon, and likewise, the moon exerts this force back on the Earth. This formula gives you the force that they both exert on each other, because gravity is two-way. Now, this force acting on the moon's mass is enough to cause a noticeable change. The Earth, however, is 100 times more massive, and so this force that the moon exerts on the Earth is not enough to move the Earth. The Earth is so much bigger that the force the moon puts back on it doesn't make the Earth move. It does move our tides, but not the Earth's core. This is good because if the Earth did move around too much, then we'd be knocked around in our solar orbit and burn and or freeze. Before we utilize this number, I also will point out this interaction, the fact that our moon's gravity is not enough to disrupt Earth's orbit, is the reason why Earth is a planet and Pluto isn't. You know how Pluto's teeny tiny? It's so tiny that its own moon is not that much bigger than it. Like, Earth and our moon, pretty noticeable difference. But Pluto and Charon, not that different. Their masses are similar enough that the force Charon exerts on Pluto is enough to make Pluto budge. And so rather than one cleanly orbiting the other, they orbit each other in a weird semicircle thing.
Until they collide.
Eventually, all matter is eventually drawn towards all other matter. So eventually they might collide. Right now, they're just in this weird dance. And since one does not cleanly orbit the other, Pluto's not a planet. They changed the rules so that that's a disqualifying factor. They had to make some kind of rule like that because there are moons in this solar system that are bigger than Pluto.
Wait, how much longer did they find Pluto's moon than after they found Pluto?
Pluto took a lot of time and effort to find. I've actually been to the lab where they first found it. And it was only after a lot of time spent in the darkest lab telescope that they had. So I imagine finding Charon would take the same amount of effort, like to see it, because the problem was seeing Pluto. It's so far, it just doesn't send much light our way. And Charon's smaller, so seeing it would be even harder, but once we knew Pluto was there and where to look, I imagine finding Charon was still measurably easier. Not easy, just easier. Now, that force of gravity acts as a centripetal force on the moon, causing the moon to orbit, which means we get an interesting interaction where we can set the gravity formula equal to the centripetal force formula. That's because the gravity is acting as centripetal force. Some real force always has to play the role of centripetal force. And if the gravity is the centripetal force, we can plug that formula in for Fc and then set it equal to m times ac, which is the other centripetal force formula. Centripetal force equals mass times centripetal acceleration. Centripetal acceleration equals v squared over r. So I just kind of combined the entire centripetal force formula here and set it equal to the gravitational formula. This is the main crux of any orbit question. And the scenarios where in space, gravity acts as a centripetal force. So that gravity acts on the mass of the moon and causes it to orbit the Earth at a certain distance at a certain speed. So put this in your notes. There's orbit questions on your homework. There will be one orbit question on test 2. We will practice it. Just want to make sure you know, if it involves orbiting in space, main thing to do is set gravity equal to centripetal force. I will also point out that these R's are the same. On this side, R is the distance between the center of mass of the moon and the Earth. On this side, this is the radius that the moon orbits the Earth at, which is the same thing. Gravity is acting as the centripetal force, so the gravitational radius is the same as the orbital radius. So it's the same R, which means you can get into some interesting cancellation shenanigans. The other thing I want to point out, in the way that I've written this, is that on the left, you've got two masses, Earth and Moon, and one of those two masses is also on the other side, because this force is acting on the object, causing one of them to orbit the other. So the rule is, the mass in the centripetal force formula is always the object that is doing the orbiting. The moon is the object that is accelerating centripetally. Therefore, it's the moon's mass that is multiplied by centripetal acceleration. So on this side, the mass question mark is the moon again.
We just gotta find velocity.
Yep, we can use this to figure out how fast the moon moves. We've already figured out this, so I'm just going to input that number we found. 1.99 times 10 to the 20. That's going to be equal moon mass. Keep writing that number wrong. 36 times 10 to the 22nd. V squared. And again, that radius is the same radius we used before. They both ask for the distance between the centers of the two objects. Lots of big numbers, but if you do it right and take the correct square root, this should give you about 1,018 meters per second. The moon is booking it. That's about Mach 3, 3 times the speed of sound. If the moon was moving any slower than this, it would drift towards the planet, and then we have problems. If the moon moves any faster than this, it drifts further away from the planet, and then we still have problems. less urgent ones. Questions? All these same principles apply to anything orbiting anything else in space. So same thing for the satellites orbiting Earth, same thing for Earth orbiting Sun. If a comet starts orbiting us, which is a type of question I might ask, then same principles, FG equals FC.
Why did you use r squared in the centripetal force?
I did not. This is R. Over here we
meters,
squared R.
my bad.
Yeah, sorry, that wasn't, converting it there wasn't squaring it, it was turning it into meters from kilometers. Very last thing I'll point out, there is another version of the centripetal force formula, because you could do the rotational one instead. Instead of v squared over r, it's omega squared times r, and that would tell you the moon's angular speed, radians per second instead of meters per second. So this is its linear speed. This is the speed it wants to rocket away in a straight line at. If you use this version instead, it would tell you, radians per second, how many degrees it moves through every second around the planet. And just for a sense of scale, this answer is actually teeny tiny. Moon is moving very slow angularly because it takes it a full 24 hours to do a single lap. So orbits tend to have very low angular speeds, but very high linear speeds. The Earth's even slower. It takes the Earth a whole year to do a lap around the sun. The Earth's angular speed is slow as dirt, but its linear speed is, Mach 9. How you guys feel? We will practice this. Next week, Monday, we'll focus mostly on torque, but we will practice this. I also recommend looking over the Chapter 7 homework, making sure everything on that makes sense, and letting me know if anything doesn't make sense. And next week, we'll do more spinning stuff. Please have a nice weekend.